dry friction. The remainder of this chapter describes the effect of dry friction acting on the exterior surfaces of rigid body. Effects of dry friction. Acting on the exterior surfaces rigid bodies. We will now explain the mechanism of dry friction with the aid of a very simple experiment. Mechanism of dry friction. Consider a solid block of mass m resting on a horizontal surface as shown in this picture. We assume that the contacting surface have some roughness. Our assumption: contacting surfaces have some roughness. The experiment involves the application of a horizontal forces P which continuously increase with 0 to a value sufficient to move the block and give it an appreciable velocity. The free body diagram of the block for any value of B is shown in the picture B, this picture, free body diagram, where the tangential friction force exerted by the plane on the block is labeled F. F, tangential friction force. Exerted by the plane on the block is labeled as F. The friction force acting on the body will always be in a direction to oppose motion or tendency toward motion of the body, as we said before. There is also a normal force, which is the case of equals to mgn. Normal force, in this case, equals to mg. And the total force are exerted by the supporting surface of the block is the resultant of N and R. A magnified view of the irregularities of the mating surface were shown in the picture here. Help us to visualize the mechanical action of friction. Support is necessary, intermittent, and exists at the mating humps. The direction of each of the reaction on the block R1, R2, and R3 as shown in the picture. depends not only on the geometric profile, the irregularity, but also on the extent of local deformation at each contact point. The total normal force N is the sum of the N component of R's, and the total friction F is the sum of the T component of R's as shown in the picture. T component in this direction, and N component shown also in the picture. When the surfaces are in the relative motion, the contacts are more nearly along the top of humps, and the T components of R's are smaller than when the surfaces are at rest relative to one another. These observations help us to explain the well-known fact that the force P necessary to maintain motion is generally less than the required to start the block when the irregularities are more really in mesh. If we perform the experiment and record the friction force F as a function of P, we obtain the relation of the force P and F as this picture. Consider this picture. When P is 0, equilibrium requires that there no be friction force. As P is in increase, the friction force must be equal and opposite to P as long as the block does not slip. If this part static no motion part as stated here. During this period, the block is in equilibrium and all forces acting on the block must be satisfy the equilibrium equations. Finally, we reach a value of P which causes the block to slip and to move in the direction of the applied force. Kinetic friction. At the same time, the friction force decreases slightly as shown here. And abruptly. It then remains essentially constant for a time, but then decreases still more as the velocity increases. This is the relation between the applied force and the friction force. The next section is about static friction.